Hello, I'm Norman Wildberger. In the last few videos, we've been talking a lot about spaces of polynomials, which are lovely applications of our ideas from linear algebra. We're going to continue with that and have a look at some other bases of polynomial spaces today. In particular, we're going to talk about Lagrange bases, or sometimes called Lagrange interpolation polynomials. We're going to talk about Bernstein polynomials, about Chebyshev polynomials, and a new remarkable family of polynomials called spread polynomials. So our general context is we're going to be working in a familiar space of polynomials of degree 3 or less, what we're calling P3. And there's a typical element of P3. It's an abstract polynomial in powers of alpha up to third power. Now we've already discussed three useful bases of this space. The first, the standard basis, sometimes called the power basis, is just the polynomials 1 alpha, alpha squared, alpha cubed. They're the natural building blocks. Any polynomial is obviously a linear combination in a unique way of these particular four polynomials in that sequence. Then we also saw that for some purposes, especially connections with calculus, it was useful to modify this a little bit into what we call the factorial basis, where we just take these elements here and we scale them, dividing each one by the appropriate factorial. We also had a look at what we might call the Taylor basis. That's concerned with when you translate a polynomial by a particular number c, then the standard basis here gets moved to a new basis shifted by c. So it depends on c. We might call it b sub c. It's 1 alpha minus c and powers of alpha minus c. So today we're going to look at some other bases, and the first one that we're going to look at goes back to the famous French mathematician Lagrange. And it concerns the problem we've already discussed, the problem of interpolating a fixed number of data points. In other words, trying to find a smooth polynomial that goes through some fixed points. Now we've already had a look at this particular problem. We're going to look at it from a slightly different point of view today. We're going to think of these four base points on the x-axis as being fixed. And for today, we're going to just consider them to be the points 1, 2, 3, and 4. So those are going to be four fixed points. And we're going to suppose that our four data points have y values associated to each one of these. So we have y1 there, a y2, a y3, and a y4. And we're interested in finding the polynomial that goes through those 4 points. Now 4 points means that generally a cubic polynomial will suffice. So we're working in our space P3. Those are specifically the 4 points that we want to go through. And what we're doing now is thinking about trying to find a general formula. We know we could find such a polynomial by solving a system of linear equations, but if you had to do this every day for different y values, you might want to have a formula instead of having to go through that procedure. That's what the Lagrange interpolation polynomials allow us to do. So now we're interested in studying this general polynomial p of x at these particular 4 values. And so it's natural to consider a mapping that takes a general polynomial p and takes it to the vector whose elements are the 4 values of that polynomial at our 4 distinguished points. This is a way of transforming our abstract 4-dimensional space of polynomials to specific space of 4 vectors, column vectors with 4 elements. This is the kind of thing we like to do in linear algebra because this is a linear transformation. But it's more than just that, it's actually an isomorphism. I remind you what that means is that it's a bijection between this space and this space, which is also a linear transformation. Why is it a bijection? Well, if you think about this map and ask what is its kernel, in other words, what vectors or what polynomials go to the 0 vector? We're asking which polynomial has the property that its values at 1, 2, 3, and 4 are all 0. Well, a polynomial of degree 3, if it has zeros at 1, 2, 3, 4, it must be the 0 polynomial. So the kernel is just 0. And the image is all of V4 by the rank nullity theorem. I remind you that the rank of a transformation plus the nullity is the dimension of the space that we started with. So we're starting with a space of dimension 4, mapping to a space of dimension 4. If the kernel has dimension 0, which it does, then the image must have dimension 4. So that's telling us that this must be an onto or surjective map because it's one-to-one or injective. So this is a sketch of why this is an isomorphism. This is a legitimate now identification of polynomials to vectors. A matching up. That's what an isomorphism does for us. So in terms of this linear transformation from polynomials to vectors, which is sort of an evaluation mapping, the Lagrange polynomials are easy to describe. What they are is just those polynomials that get mapped to the standard basis vectors in V4. So E1, E2, E3, E4, the standard basis vectors in V4, those are the vectors with a single 1 in one entry and zeros everywhere else. And so the polynomial P1 is defined to be that polynomial which is mapped or sent to E1. What's that look like? What does it mean? Well, it means that if you evaluate the polynomial P1, at 1 you're going to get 1, and at 2, 3, and 4 you must get 0. That's what it means for 5P1 to be equal to E1. And so P1 has this shape right here when you draw its graph as a function. It has the value 1 at the point 1, and 2, 3, 4, it's 0. It's not too hard to write down what that polynomial must be because of the fact that if we know its zeros, we pretty well know the polynomial. A polynomial of degree 3, which has 3 zeros, 2, 3, and 4, must be a multiple of alpha minus 2, alpha minus 3, alpha minus 4. And that multiple is determined by the fourth condition that its value at 1 be 1. So in order for this polynomial to have the value 1 at 1, it means the denominator here should be the same as what we get when we plug in 1 in the numerator. So that's what we're doing. We're just dividing by 1 minus 2, 1 minus 3, 1 minus 4. That ensures that when we set alpha equal to 1, we get 1. So this polynomial is the polynomial P1. It has value 1 at 1 and 0 at 2, 3, and 4. That's the first Lagrange polynomial in this situation. And then there's also P2, P3, and P4, which have the properties that they go through 3 of these 4 points on the x-axis and have value 1 at one of the others. So for example, P2, this one here, is the polynomial which is 0 at 1, 3, and 4 and has value 1 at 2. It's the polynomial that's sent to the second basis vector under this evaluation mapping. So we can write down very explicit formulas for both P1, P2, P3, and P4. And with these Lagrange interpolation polynomials, we can solve the Lagrange interpolation problem very simply. So we've constructed a new basis for our space P3. The Lagrange basis are 4 polynomials P1, P2, P3, and P4. Now this basis actually depended on our choice of original points on the x-axis, the points 1, 2, 3, 4. If we chose those points in a different way, we would get a different Lagrange basis. So now, suppose we want a polynomial P which takes the values y1, y2, y3, and y4 at the points 1, 2, 3, 4, respectively. What do? We just create P by taking an appropriate linear combination of these 4 polynomials. We take y1 times P1 plus y2 times p2 plus y3 times p3 plus y4 times p4. There it is explicitly, so there's y1, that was the polynomial p1 that I wrote down before. There's p2, a similar kind of formula. There's p3, there's p4. So there's the polynomial function p of x, a linear combination of p1, p2, p3, p4 with coefficients y1, y2, y3, and y4. And why does this polynomial do the job? Well, suppose we substitute into p the value 1. What happens? Well, these three polynomials are 0 at 1. So they contribute nothing. That's all 0. And p1 of 1 is, by definition, 1. So the output at 1 is just y1. Similarly, if we looked at the output at, say, the point 2, at the point 2, these three polynomials have the value 0, and this one has the value 1, so the output is y2. Similarly, the output at the point 3 is y3, and the output at 4 is y4. So this is the interpolation polynomial that goes through our 4 data points, depending on y1, y2, y3, y4. And what we're really doing is we're really using this particular basis for our space of polynomials. Now let's have a look at another interesting family of polynomials called the Bernstein polynomials. These are involved with the problem of uniform approximation to a continuous function. So the setup is we're on a particular interval, say the interval 0, 1 for simplicity, and we have some continuous function represented here in black, the function f of x. So going up here, then there's a little sharp point, going straight down, then straight across. That's a continuous function, but it's clearly not a kind of polynomial function because it's got this abrupt non-smooth point here, another sort of abrupt non-smooth point here, or corner. Polynomials never have corners. Nevertheless, we might want to approximate this function by a polynomial because polynomials are easy to work with in our computers. So we want a polynomial function, p of x, that approximates this continuous function uniformly on 0, 1. What does uniformly mean? Well, it means that the approximation is good throughout the interval. We don't want just a good approximation on part of the interval and a lousy approximation on the rest of it. We want a good approximation on the entire interval. We can say that in the following way, that the function f of x that we start with, the polynomial that's approximating it, that difference in absolute value should be less than 1 over n for some fixed n for all x in the interval. So for example, n could be 100. We're interested in getting a polynomial which agrees with f of x within 100 all the way through. Alright, so how do you find or write down such a polynomial p of x to a certain degree of accuracy given the function f of x? Well, the Bernstein polynomials help us to do exactly that. So the Bernstein polynomials naturally form a kind of triangular structure which has a lot to do with Pascal's triangle. And it's best to think of them as being in layers. So there's kind of the degree 0 Bernstein polynomial, which is just the polynomial 1. And then there are two linear Bernstein polynomials, 1 minus alpha and alpha. And all the other Bernstein polynomials are products of powers of this one with powers of this one, times some coefficients. So the degree 2 Bernstein polynomials, there's 3 of them. One of them is 1 minus alpha squared. Another one is 2 times 1 minus alpha alpha, and the other one is alpha squared. And the degree 3 Bernstein polynomials, 1 minus alpha cubed, 3 times 1 minus alpha squared times alpha, 3 times 1 minus alpha alpha squared, and just alpha cubed. So what's the pattern? Well, we're starting off with the pure power of 1 minus alpha to the third power. And as we move, we decrease the power of 1 minus alpha and increase the power of alpha, until at the end we just have a pure alpha cubed power. And the other ingredient is the coefficients Here they are 1, 3, 3, 1. You'll recognize that, I hope, as just a line of the Pascal's triangle. Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. So the coefficients are just Pascal coefficients, and otherwise we're talking about powers of 1 minus alpha and alpha as we move across, lowering powers of 1 minus alpha, increasing powers of alpha. So these are the Bernstein polynomials, and let's just give them some names. So if we look at just the third degree polynomials, P3, there are 4 of them, and we'll give these 4 some names. So we'll call it this one B03, the next one B13, the next one B23, and the next one B33. So they are explicitly. And those 4 polynomials form a basis of our three-dimensional space, the Bernstein basis. And we're just working here with three-dimensional space, but you could look at four-dimensional space also. So in four-dimensional space there would be 5 Bernstein polynomials. And in 5-dimensional space there would be 6 Bernstein polynomials. And the pattern is exactly the same. All right, how do we see that this is actually a basis, that we can write any polynomial uniquely in terms of those 4? Well, before we answer that, let's have a look at what these polynomials look like. So, degree 0, there's just one polynomial whose graph is just a constant function. In degree 1, there are 2 polynomials whose associated functions are 1 minus x, which is this one, and x, which is this one. In degree 2, we have x squared, 2 times 1 minus x times x, which is that parabola there, and 1 minus x squared coming down like that. In degree 3, our favorite example, we have our 4 Bernstein polynomials, B0, B1, B2, and B3, where I'm suppressing the second index because we're already acknowledging that we're in degree 3. And in degree 4, there's 1 minus x to the 4th. Then there's 4 1 minus x cubed times x. That'll be that one in green. Then the middle one, 6 1 minus x squared times x squared. It'll be that one there, black. 4 times 1 minus x times x cubed. That one there. And x to the 4th, like that. That's the kind of pattern that the Bernstein polynomials exhibit. So here's a way of seeing that the Bernstein polynomials of a certain degree really do form a basis for that corresponding polynomial space. Here's our familiar Pascal's triangle. So I remind you that its main property is that any element here is the sum of the 2 elements directly above it. So 2 plus 1 is 3, 3 plus 1 is 4, 3 plus 3 is 6, and so on. That's how you build Pascal's triangle. Over here I've written down the Bernstein polynomials without the coefficients. So what we might call the unnormalized Bernstein polynomials. So instead of having a 1, 2, 1 and a 1, 3, 3, 1, I've just ignored the 3's and the 2's. And when one looks at this, it's interesting that there's a very nice property that this pattern has, which is a little bit similar to this one, but in sort of the opposite direction. And the property is that if you take 2 elements, say like these 2 that are adjacent, and you add them up, then what you get is the element above it. For example, suppose you take this 1 minus alpha squared times alpha and this 1 minus alpha times alpha squared. Then here is a common factor that both of these have. And otherwise, this one has a 1 minus alpha extra factor, and this one has an alpha extra factor. And when you add the 1 minus alpha to the alpha, you get just 1. Which is why this plus this equals this. And that's repeated throughout the table. So this plus this equals this, this plus this equals this, and so on. So now we can see roughly why this is going to be a basis. Let's suppose that we've convinced ourselves that these 3 polynomials are a basis of P2. And we want to convince ourselves that these 4 are a basis of P3. Well, P3 consists of the P2 basis vectors, the things of degree 2 or less, plus 1 more, alpha cubed. So we know that these 4 are a basis. But these 4 here generate these 4, because this plus this is this plus this is this plus this is this. So anything that we can express with these 4, we can also express with these 4. That's a sketch of a proof why these 4 form a basis for P3. And similarly, these 5 will form a basis for P4 and so on. So in general, the n plus 1 Bernstein polynomials of degree n, we might call them B0n, B1n, up to Bnn, they form a basis of Pn, space of polynomials of degree n or less. While this is not a course in numerical analysis, let me at least explain briefly how the Bernstein polynomials are used to approximate a given continuous function on an interval. So we'll suppose that f of x is some continuous function on the interval 0, 1. Here's our picture, the interval 0, 1. Here's our continuous function f of x in black. We'd like to approximate that by a polynomial, say a polynomial of degree n. Here's the formula that works. It's a sum from k equals 0 to n of some numbers times the Bernstein polynomials of that degree. So P0n, P1n, P2n, and so on, all of those added up together with coefficients or weightings. And what are the weightings? Well, they're just the function's values at the points k over n. What are these numbers k over n as k goes from 0 to n? Well, they're just what you get when you split up the interval 0, 1 into n equal pieces. Here I've divided up into 3 equal pieces, giving 4 endpoints. 0, 1, 2, 3. So that's 0 over 3, 1 over 3, 2 over 3, 3 over 3. So in the case of n equals 3, the formula would tell us that we're going to take the first, or the 0th Bernstein polynomial times the function's value at 0, namely that value, plus the first Bernstein polynomial times the function's value at 1/3, namely that value, plus the second Bernstein polynomial times that value, and the third Bernstein polynomial times that value. So we're summing up the 4 Bernstein polynomials with weightings, and the weightings are just the given function's values at those equally spaced points. It's a beautiful formula. It's very kind of natural. And then it's a theorem that, okay, here's our general formula for what we're doing, that as n gets large, this becomes a good uniform approximation to the function. So, okay, for, 4 points there, it's not going to be such a great approximation. But when you take 10 points or 100 points, you're going to end up with quite a good approximation to the function f of x in terms of a polynomial of degree 10 or 100. So that's how another basis, the Bernstein polynomial basis, helps us in a very explicit and practical problem in numerical analysis or calculus. And it's really helpful to think in terms of taking linear combinations of these 4 basis vectors in this space. Now let's have a look at the Chebyshev polynomials, which play an important role in approximation theory and integration theory, and are also intimately connected with trigonometry. They can be defined in a number of ways, but probably the simplest is to use a recursive definition. So we define t sub 0 to be 1 and t1 to be alpha. And then after that, they're defined by this formula here, that tn plus 1 equals 2 times alpha times tn minus tn minus 1. So it's a good exercise. You can compute. The first 5 are here. 1 alpha, 2 alpha squared minus 1, 4 alpha cubed minus 3 alpha, then 8 alpha to the 4th minus 8 alpha squared plus 1, and the fifth one is 16 alpha to the 5th minus 20 alpha cubed plus 5 alpha. And they go on. Now you've seen at least one of these before. This one here, T2, comes about from the double angle formula for the cosine function. So I remind you that cosine of 2 theta is 2 times cos squared theta minus 1. So we think of this as being a polynomial in cosine theta. It's really the polynomial 2 alpha squared minus 1 right there. A little bit less familiar formula, but also a valid one, is this formula for the cosine of 3 times an angle. Cosine 3 theta equals 4 cosine theta cubed minus 3 cos theta. This is a polynomial in cosine theta, and it's exactly this polynomial. So in general, the nth Chebyshev polynomial, Tn, is what you need to express cosine n theta in terms of cosine theta. And the polynomials have a very pleasant pictorial description when you look at their values between minus 1 and 1 on the x-axis. It turns out they all have values between y equals 1 and minus 1. So t of 0 equals 1, well, that would be just that constant function. T of 1 is the function alpha, or x. T2 would be this polynomial right there. T3 is this one here. T4 is this one in red. And the higher Chebyshev polynomials all have graphs which bounce around uniformly from the top and the bottom of this basic box. So it's a rather pleasant picture. So if we go back to our favorite space P3, polynomials of degree 3 or less, then we now have a new basis. We can call it the Chebyshev basis, consisting of the polynomials T0, T1, T2, and T3. They do form a basis. It's pretty easy to see because this one is of degree 0, this one is degree 1, this one is degree 2, and this one is degree 3. So a kind of question that's sort of interesting is, how do you go from one basis to another? That question has different aspects, but one way of saying it is, how do we write the power basis, what we've been calling B, consisting of the functions 1 alpha, alpha squared, and alpha cubed, in terms of the Chebyshev basis C up here? What we do know is how to write the Chebyshev polynomials in terms of the standard, the power basis. We know that T0 is equal to 1. We know that T1 is equal to alpha. We know that T2 is 2 alpha squared minus 1, hence that row there. And we know that T3 is 4 alpha cubed minus 3 alpha. So we can express all those 4 equations in one matrix equation, relating this abstract vector of the 4 basis elements of the Chebyshev basis with the 4 basis elements of the power basis. And this matrix converts from this basis to this basis. So if we wanted to express the alphas in terms of the t's, then we're back to our fundamental problem in linear algebra of how to invert a linear system. And what we do is we multiply by the inverse of this matrix. Or if you like, we row reduce the corresponding system. Here's the inverse of the matrix. And so this vector over here is this matrix times this thing over here. From which we can read off, for example, that, say, alpha squared, the third row, would be 1/2 T0 plus 1/2 T2. While alpha cubed would be 3/4 of T1 plus 1/4 T3. So this kind of problem where we're converting from one basis to another, or perhaps converting from the coordinates of some polynomial from one basis to another is really a linear algebra problem that involves inverting a linear system. It would take quite a lot of lectures to explain how the Chebyshev polynomials are useful in approximation theory and in integration theory. And it really doesn't belong in a linear algebra course, rather in a calculus or numerical analysis course. But what I do want to tell you about is another basis which replaces the Chebyshev polynomials from a more modern point of view. This is the theory of spread polynomials, which arise in rational trigonometry. And a clue as to where they're coming from is to go back to the basic trigonometric identity that is at the heart of the Chebyshev polynomials. So remember the double angle formula for cosine. Cosine 2 theta can be expressed as cos squared theta minus sine squared theta. And by replacing the sine squared with 1 minus cos squared, we can write that as 2 cos squared theta minus 1. And that's where that second Chebyshev polynomial came from. It's natural to ask, well, what about the corresponding formula for sine 2 theta? The double angle formula for sine 2 theta is 2 cos theta sine theta. So we might ask, well, let's try to express that as a polynomial in sine theta. Unfortunately, it doesn't work quite so well because when you replace cosine theta, you have to use the square root of 1 minus sine squared theta. So although you can express this as a function of sine theta, it's no longer a polynomial equation. So there's a bit of an asymmetry here between the cosine and the sine. But it turns out that if you square this, then you have a nice expression. So suppose we just square this relation, then we get sine squared of 2 theta is 4 times 1 minus sine squared theta times sine squared theta. In this relation, there are no square roots anymore. And we see that sine squared 2 theta is a polynomial in sine squared theta. So sine squared 2 theta is a polynomial in sine squared theta. And that polynomial is 4 times alpha times 1 minus alpha. So if you replace alpha with sine squared theta, then you're getting sine squared of 2 theta. Now this is a very important polynomial, not just for the fact that it's the second spread polynomial, it's also important map in chaos theory called the logistic map. So this particular function arises in mathematics in a number of different ways. But here we see that it's just the first of a succession of polynomials. But we can play the same game for sine squared of 3 theta. That also turns out to be a polynomial in sine squared theta, which is the third spread polynomial. So by looking at sine squared theta instead of cosine theta, we get a different but related family of polynomials, which are also very interesting and which are in many ways superior to the Chebyshev polynomials. Let's have a closer look at them. Although we were motivated by that trigonometric relation involving sine squared theta and sine squared 2 theta, that's not what we're going to use to define the spread polynomials. Because remember, we're working in a purely rational domain. In pure rational domain, cosine and sine don't play an obvious role because they require a theory of irrational numbers to get going. And also because in practice, most calculus courses these days avoid rather carefully saying exactly what cosine and sine and other circular functions are really defined to be. Check out your calculus course. Probably it's deficient in this context. Many courses are. So there's a lot of ambiguity around the subject of traditional trigonometry, around circular functions, their proper definitions and properties. It's better to avoid all of that and stick to a recursive definition of the spread polynomials. So here's actually how we define them. We start with this particular definition that S0 equals just the zero function, and S1 is the polynomial alpha. And then Sn plus 1 is 2 times 1 minus 2 alpha times Sn minus Sn minus 1 plus 2s. It's a slightly different kind of recursion than what's usually found in this subject. And the spread polynomials have somehow slipped through the cracks of the theory of special functions. They are, however, very important special functions, and I predict they will be a great source of study in the next century. The second spread polynomial we've already seen. There it is there, 4 alpha times 1 minus alpha. The third spread polynomial, alpha times 3 minus 4 alpha squared. The fourth one is 16 alpha times 1 minus alpha times 1 minus 2 alpha squared. And the fifth one is alpha times 5 minus 20 alpha plus 16 alpha squared, all squared. So these polynomials were introduced in 2005 in my book, Divine Proportions, Rational Trigonometry to Universal Geometry, which of course should be compulsory reading to all students of mathematics. You can find some downloads and more information at wildegg.com. So the spread polynomials, these ones right here, play a very analogous role to the Chebyshev polynomials, but instead of on the interval minus 1 to 1, we're working in the interval from 0 to 1. The x-axis from 0 to 1, the y-axis from 0 to 1. And otherwise they have a behavior which is pretty similar to that of the Chebyshev polynomials. There's the 0 polynomial, there's S1, S2 is the logistic map in green, S3 like this, S4 like this, and higher S's, they all start down here, they all bounce up and down just like the Chebyshevs do, and eventually they either end up here or here depending on whether n is even or odd. The spread polynomials have a direct and pleasant relationship with the Chebyshev polynomials, given by this relation here. So this allows us to apply the spread polynomials for a lot of applications where Chebyshev polynomials are used, and conversely. So in terms of approximation or integration theory, the spread polynomials are pretty well much the same as the Chebyshev polynomials. However, the spread polynomials have some interesting advantages. One of them is a beautiful factorization theorem discovered by my student Suxiang Guo in 2005. He noticed that the nth spread polynomial factors into a bunch of factors. Each of them are also polynomials. The phi sub k's, where k runs over all divisors of n. And this means product. So the product over all k dividing n of certain other polynomials called phi sub k's. And here's another observation made by my colleague Mike Hirschhorn, also in 2005, that show you how you can write down the coefficients of the spread polynomials pretty easily. Actually not about the spread polynomials, but actually some normalized versions. So if we replace Sn with Sn alpha over 4 times 4 and call that Sn star, then here's how we write it down by a certain line in this array. And how do we get this array? Well, it comes from Pascal's array. A little bit different with diagonal entries, the usual Pascal rows, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. And then to go from this to this, what we do is first of all ignore that first column. And secondly, we replace each element here with the sum of itself and the number directly above it. So 6 plus 3 is 9, so there's a 9 there. 5 plus 1 is 6, there's a 6 there. 1 plus 0 is 1, so there's a 1 there, and so on. And then every second column here gives us, with alternating plus and minus signs, the values for these modified or normalized spread polynomials. So I predict that the spread polynomials are going to be a big source of study in special function theory in the decades to come. So if you want something really interesting and new to work on, there's a very rich vein of things to be studied here with these spread polynomials. Now let's have a look at how they work in terms of a new basis for our spaces of polynomials. So if we return to our space P3 of polynomials of degree 3 or less, then here's a new basis. We could call it the spread basis. There's S1, there's S2, there's S3. This isn't exactly S0 because S0 was 0. So we're going to just use the constant function 1 as the first entry there. And here, for example, is the relation between the 4 elements in this basis and the 4 elements in our power basis or standard basis. And one of these rows just express how we write the spread polynomial as a linear combination of those powers. So for example, S2, the logistic map, is 4 alpha minus 4 alpha squared. So an interesting kind of problem is, well, how would you invert this? How would you write the powers in terms of the spread polynomials? It's a question of inverting this 4 by 4 matrix. There it is there. And now that allows us to read off, say that alpha squared is equal to 1 S1 minus 1/4 S2. And we can put these various bases together and compare them. Once we've got things in terms of matrices, then the matrix multiplication works very smoothly to allow us to do calculations without a lot of worry. In fact, we can get our computers to do these things very efficiently for us. So for example, suppose we wanted to write the Chebyshev basis in terms of the spread basis. So here's the Chebyshev basis elements in terms of the power basis. That's the matrix that we had before. And now we can replace this vector of basis vectors from here by this matrix times this vector of spread polynomial basis vectors. And so then to get the final answer, it's just a question of multiplying these two 4 by 4 matrices together, giving us that one. And then we can conclude, for example, that T2, the third one here, would be minus 2 plus 4S1 minus 2S2. So the moral is, once we can convert a problem into matrices and vectors, then computationally things are very simple and they proceed very smoothly because, for example, we can get our computers to calculate this kind of product very quickly. So that's very good. Let's have a look now at some exercises for you to think about. So our first two questions have to do with Lagrange polynomials. So first question is to find a polynomial in P3 which satisfies P1 is minus 1, P of 2 is 1, P of 3 is 2, and P of 4 is minus 1. And the second one is to find polynomial satisfying P of minus 1 equals 2, P of 0 equals 3, P of 2 equals 1, and P of 5 equals 4. Here are two exercises having to do with the Bernstein polynomials. This one is to show that B03 plus B13 plus B23 plus B33, the sum of those four, is the polynomial 1. Try to generalize that. And here another useful property of the Bernstein polynomials, that Bkn evaluated at x is the same as Bn minus Kn evaluated at 1 minus x. Next exercise, to express this particular polynomial, 1 plus alpha squared plus alpha cubed. First of all in the Chebyshev basis, and secondly in the spread basis, which means write it as a linear combination of the Chebyshev polynomials and write it as a linear combination of the spread polynomials, all in P3. Here's an interesting exercise relating to the spread polynomials. I'm asking you to show that S2 of S2 of x equals S4 of x, and S2 of S3 of x equals S3 of S2 of x equals S6 of x. Can you generalize that? And finally, can you express the Bernstein polynomials B03, B13, B23, and B33 in the Chebyshev and spread bases of P3? So we've had a good look at spaces of polynomials interpreted as functions. Functions on, in fact, the rational number line, or sometimes on intervals. However, that's in fact only half of the story with polynomials. There's another entirely different world in which polynomials play a crucial role. That's not a continuous world like we've been talking about here with functions. It's rather a discrete world of sequences. Now, sequences are just as important in mathematics as are functions. And what we're going to be doing in the next lecture or two is investigating another aspect of polynomials and linear algebra of them, relating to sequences. So we'll discover some beautiful classical formulas also relating to that. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.